Hey math fans, we're on section 2.4.1. Let's get started. In this section, we're going to be graphing square root functions and cube root functions. And here are some key concepts that we have already gone over. One is the restricted domain. Sometimes we're going to have to say, you know what, x can't be equal to these certain values. And remember, the range is all the y values. Sometimes the range will also need to be restricted. Here's a quick review of what an increasing and decreasing function is. So this is what a square root function looks like. We're going to start calling this the parent function for the square root, and we're going to be shifting this function and transforming this function based off of the equation that we're given. This is what a cube root function looks like. In a cube root function, a new vocabulary term that I want to go over right now is called a point of inflection, and that's where the curve changes concavity. And it's really easy to find the point of inflection because it's a lot like finding the vertex in the quadratic. Notice we're still using the same letters, h and k. So the point h comma k will be the point of inflection, or where the graph changes concavity. Here's some common errors and misconceptions. This is what the square root function looks like. Well, why does it look like this? Well, first of all, notice the domain is restricted because we can't have any negative numbers inside the radical. The lowest number is going to be 0. The square root of 0 is 0. Now, when we plug in numbers for x, like let's say 16 or 100, we're going to be taking the square root of that. So notice it goes up kind of slowly. So here are some of the points on the graph. 16, comma 4, because the square root of 16 is 4. 49, comma 7. 100, comma 10. Again, we're taking the square root of the x values, and then the y value is being graphed. This is what the cube root function looks like. Now notice there are negative values. Why are there negative values? Well, because you can take the cube root of a negative number. In other words, we can take the cube root of negative 8. You can ask yourself, what number times itself 3 times will equal negative 8? And the answer is negative 2. Negative 2 times negative 2 times negative 2 will get you negative 8. So you can take the cube root of a negative number. Of course, you can take a cube root of the positive 8 as well and get positive 2. So the graph has a domain of all real numbers. Example 1, the function y equals 0.176 times square root of the quantity x plus 30 has a restricted domain of negative 30 less than x less than 0. And it says determine the restricted range for the function and use a graph to estimate the value of y when x is equal to negative 10. So why does it have a restricted domain at negative 30? Well, if it was any less than negative 30, like negative 40, you would have a negative number inside the square root symbol. And you cannot take the square root of a negative number and have it be a real number. Here's what the graph looks like. Notice how it begins, or it starts there at negative 30, or that's going to be the lower boundary for our domain. And it has a y-intercept of 0,0.964. Then the problem says, well, why don't we just try and estimate? What would it be when x is equal to negative 10? Well, according to the graph, it's going to be less than that 0.964. And how could you get an exact value? Well, you could just plug in x equals negative 10 into the original function, and you'll get a y value of 0.787. So we were correct. It was a little bit below the 0.964 value for the y-intercept. Example 2 says compare the domain range graph and points of inflection for these two functions. Now notice one of them is the parent cube root function, but the other one says it's negative 4 times the cube root of x plus 2. Well, let's see how these differ. So the point of inflection for the parent function is going to be 0, 0, because there is no h value there, and there is no k value either, but they're both going to be 0. So that's where the concavity is going to change. A little bit different for the other function. What would make the square root 0? The answer is 0. And then when we plug in 0, we get 2. So its point of inflection will be 0, 2. And here's what the two graphs look like if we were to plug in several points and start graphing these out. Notice that the parent function we're pretty familiar with. I showed you that at the beginning of the video, but the second function has kind of been flipped upside down, and that's due to the negative 4 that's out in front. It's in essence flipped the graph of this. Also notice that it's been shifted up 2 because of that positive 2 at the very end of the function. Example 3 says, the Stevens family is building a rectangular in-ground pool. The depth, length, and width will all be related as shown in the diagram. And hopefully you remember that volume is equal to length times width times height. We're going to be multiplying these 3 dimensions together. And then we can get the depth as a function by taking the cube root. And we actually get a function where it's 1/2 the cube root of the volume. First thing we're going to do is determine the domain. Well, they don't want to have anything less than 1,000, so that's going to be our minimum boundary for our domain, and then the maximum will be 11,000. So we're going to say that V is between 1,000 and 11,000, and that will be our domain. So to get the range, well, we need the Y value for our minimum domain, which is 1,000. So let's plug in 1,000. Cube root of 1,000 is 10. We're going to get a depth of 5. How about for 11,000? We substitute that value in, and we're going to get approximately 22.2 as the cube root of 11,000. Multiply that times 1/2, and we get approximately 11.1. So our range is going to be from a depth of 5 to 11.1. And here's a graph of this particular problem. And that's going to do it for this section. We'll see you in class.